Welcome to the Deep Dive. Today we're tackling artificial intelligence.
Yeah, AI. It's everywhere.
We've got a great source here, Artificial Intelligence Basics, a non-technical introduction.
And the goal is really to give you a shortcut, right?
Yeah.
A way to understand this complex field.
Exactly. No getting bogged down in super technical jargon.
We know you might have different backgrounds, some techie, some not.
So we'll focus on the key ideas, what they actually mean in the real world.
You're here to get smart, fast,
Yeah.
hopefully have a few aha moments.
Right. So our mission, give you a solid foundation in AI, the history, the concepts, the future.
Let's dive in.
Okay, so just how pervasive is AI? It feels kind of new, but it's not really.
Now, it's more like the next step in automation. Goes way back.
Like Henry Ford kind of automation.
Precisely. AI is just extending that trend, pushing efficiency further.
The source mentions Zoho's origin story, actually.
Oh, yeah. How so?
That tension between automation for big companies and making it accessible.
Right? That egalitarian idea. How can automation benefit everyone, not just the giants?
And it's not just theory. Look at McDonald's.
They're planning AI across the board, aren't they?
Yeah.
In stores, supply chains.
Yeah, it's happening now. But the source also warns about new tech, you know.
Oh, definitely. Big risks if you don't adapt.
Think Kodak. Or taxis before Uber and Lyft.
Right. Ignoring it can be fatal for a business.
But on the flip side,
Huge opportunity if you have a solid strategy, if you understand it.
which brings us to the sheer scale.
Yeah.
The potential here is, well, it's massive.
The PwC study number is pretty mind-boggling.
What was it? $15.7 trillion added to the global GDP by 2030.
That's the one. Just to put that in perspective.
It's more than the current economies of China and India put together.
Exactly. And the study stresses AI is really only just getting started.
It's touching almost every part of life.
It could be like electricity was in the 19th century. A real general-purpose technology.
You just have to look at the big tech companies, right? Google going AI first.
Mm-hmm. And Microsoft, Amazon, Apple, Facebook, they're all pouring billions into AI.
Hiring data scientists, buying startups.
It's a huge strategic priority. And it means something for jobs, too.
How so?
More and more jobs will require some AI knowledge. Maybe not coding.
But understanding the fundamentals, what it can do, what it can't.
Exactly. Having that basic grasp is becoming really valuable.
Okay, so let's rewind a bit. Chapter 1 talks history. Back to the 50s.
Yeah, the very beginnings. With people like Alan Turing, John McCarthy, Marvin Minsky, Geoffrey Hinton, too.
Giants of the field, they started asking the big questions.
It was this mix of philosophy and the very first computers.
Like the Turing test. That was
Yeah.
Turing, right?
Right. And his goal wasn't necessarily to build AI himself.
More like defining it. What would it mean for a machine to think?
Exactly. Could it fool you in a conversation? That was the test. Processing info, communicating. Not necessarily consciousness.
And he predicted it would be passed around 2000.
He did. Which obviously didn't quite pan out.
Shows how hard prediction is in this field.
It really does. And the fact that the test is still hard to pass.
Tells you something about intelligence itself, maybe.
Yeah, the difference between just processing information and, genuine understanding. There are still competitions, like the Loebner Prize.
And philosophers like Searle chimed in too, didn't they? The Chinese room?
Right. Questioning if just running a program is understanding. Deep questions.
On a more sort of nuts and bolts level, McCulloch and Pitts were key.
Absolutely. Back in the 40s, their idea that brain activity could be modeled logically.
Using mass.
Yeah. It laid the groundwork for neural networks. Their 1943 paper was huge.
Revolutionary thinking at the time.
Definitely. Suggesting complex networks could process information, learn, even reason.
Then came the golden age, mid-50s to mid-70s.
Right. Computers got way better. Vacuum tubes gave way to integrated circuits,
So processing power exploded.
which fueled a lot of optimism, a sense that anything was possible.
But it was mostly universities driving it.
Mostly, yeah. The private sector was a bit hesitant. IBM dipped its toes in, but even they worried about, public backlash over job losses.
But the academics were busy, creating things like the general problem solver.
And Analogy, Student, and ELIZA.
Ah, ELIZA. The first chatbot.
Yeah, Joseph Weizenbaum's creation. It mimicked a therapist.
And people were amazed, right? Even though it was pretty simple underneath.
Totally. It raised early questions about how we react to AI, how human-like it seems. You can still find versions online.
But it wasn't all smooth sailing. There were disagreements. Minsky versus Rosenblatt.
Oh, yeah. A big debate about neural networks. Minsky in Papert's book, Perceptrons, in '69.
What did it argue?
It highlighted theoretical limits of the early neural nets, and that kind of put a damper on that research for a while.
Even though Rosenblatt defended his work.
Yeah, it's ironic because neural nets are now the core of deep learning. Rosenblatt's ideas came back in a big way.
The optimism back then was extreme, though. Herbert Simon predicting machines matching humans in 20 years.
Yeah, in the mid-60s. Then he shortened it to 3 to 8 years later.
He advised on 2001, A Space Odyssey, too.
Right, which definitely shaped public perception. But that optimism.
Didn't always match reality.
Exactly. Early computers, like the DEC PDP 1145, had tiny memory. And the programming languages, like Lisp, weren't common in business.
Plus, understanding language itself. Way harder than they thought.
Oh, hugely. Just figuring out which meaning of a word was intended disambiguation was a massive challenge.
Which led to the AI winter.
Yeah. Funding dried up. DARPA cut back. The Lighthill report in the UK in '73 was pretty scathing.
What did it say?
Dismissed the grandiose objectives,
Sure.
pointed out the combinatorial explosion problem.
Meaning the possibilities just grow too fast for the computers to handle.
Right. Lighthill was skeptical about image recognition, even chess playing.
Sounds like a setback.
It was a quieter period. But innovation didn't totally stop. Crucial things like backpropagation, recurrent neural networks, they came out of that time.
Then the 80s and 90s saw expert systems rise and fall.
Yeah, fueled by PCs and mini-computers. They tried to capture human expertise in specific areas.
But they didn't quite work out.
They had some success, but were often brittle, hard to update. The market cooled off. Specialized Lisp machines faded. Cold War funding ended. Another quiet spell.
But some people kept the faith. Geoffrey Hinton
He was a huge believer in neural networks. Even during the winter, he saw the potential.
realized it was computing power holding them back.
Exactly. He knew Moore's law would eventually catch up. And his 1986 paper on backpropagation, that was key.
With Rumelhart and Williams, what did it do?
It gave a much better way to train neural networks, to learn from mistakes, adjust their internal settings. Huge boost in accuracy, especially for recognizing patterns.
And other important pieces were falling into place, too.
Definitely. Fukushima's neocognitron in 1980, inspired by the visual cortex, was a precursor to today's CNNs for image recognition.
And GPUs, graphics cards.
Crucial. Initially for games, but they provided the massive parallel processing power needed to train deep learning models much, much faster.
So AI has had its booms and busts. But this current wave feels different.
It does seem more sustained, with the tech giants investing so heavily, and the real breakthroughs we're seeing.
So the takeaways from history are, it's not linear, it's interdisciplinary.
We're still mostly dealing with weak AI for specific tasks, not the strong AI of sci-fi.
And the Turing test is still this interesting benchmark.
Absolutely. A way to think about human-like interaction.
Okay, let's shift to chapter 2. Data. The lifeblood of AI.
Couldn't agree more. You need data for algorithms to find patterns, to learn. It's the fuel.
But the source warns about landmines, right? Quality, bias.
Oh yeah, critical issues. Garbage in, garbage out. If your data is bad or biased, your AI results will be too.
The Target example about predicting pregnancies? Wow.
It shows the power, definitely. Analyzing shopping habits to figure that out.
But also the tricky side. The father finding out before his daughter told him.
Exactly. Highlights the need for sensitivity, for ethics. Just because you can get an insight from data doesn't mean you should use it carelessly.
Requires real thoughtfulness.
Absolutely. Ethical considerations have to be part of the process from the start.
The source also breaks down data basics, bits, bytes, kilobytes,
Right.
all the way up to zettabytes.
Helps you get a sense of scale. A bit is on-off, a byte is a few bits.
Then megs for photos, gigs for movies, terabytes for hard drives.
And zettabytes.
Yes.
Almost unimaginable amounts of data being generated.
Where does it all come from?
Everywhere. IT devices, cloud systems like Salesforce, company databases, spreadsheets, social media, websites, apps, photos, videos, emails. It's vast.
And it comes in different forms. Structured, unstructured, semi-structured, and big data.
Right. Structured is neat, organized. Think spreadsheets, traditional databases, financial info addresses, easy to work with.
Unstructured is the opposite.
Yeah, no predefined format. Emails, text docs, videos, audio. That's most data, but it's harder to analyze.
Semi-structured is in between, like web pages.
Kinda. Has some tags, some organization, but not rigid. And then big data.
That's defined by the 3 V's, right? Volume, variety, velocity.
Exactly. Huge amounts, volume, lots of different types, variety, and generated incredibly fast velocity.
The scale is crazy. Billions of sensors, zettabytes of data predicted, Oracle calls it capital.
That 3V's framework from Doug Laney back in 2001 is still super useful for understanding it.
The volume needs new storage, like the cloud. Variety needs flexible tools. Velocity needs fast processing.
You got it.
The source also touches on relational databases, CODS model, SQL.
Yeah, Cod's approach revolutionized how we organize data, made it much more efficient, and SQL became the standard language to talk to those databases.
And Larry Ellison saw the potential early, founded Oracle.
Right. Became the market leader. But the source makes a good point.
Don't just chase the newest tech.
Exactly. Think strategically about what database fits your AI project's needs.
Okay, so you have the data. What next? The data process. CRISP-PDM.
The cross-industry standard process for data mining. It's a roadmap.
Starts with understanding the business problem.
Right. What are you trying to achieve? Then understand your data. Collect it, look at it.
Then prepare it, clean it, transform it.
Then build your model, pick algorithms.
Yeah.
Then evaluate it. Does it work?
And finally, deployment, making it usable.
Yep. But those first few steps, business understanding, data prep, they can take up to 80% of the time.
80%. Why so much?
Because data is often messy. It's in different silos, different formats, needs a lot of cleaning and organizing. Planning helps,
Yeah.
but it's often underestimated.
And you need clear success metrics from the start.
Absolutely.
Yeah.
How will you know if the AI is actually helping? What's the goal? Increase sales, fewer errors.
The AB InBev example is good using AI to predict machine failures.
Very practical. Saves money, prevents downtime, shows the real value data can create.
And Moneyball using data differently to find undervalued players.
A classic example of how data analysis can give you a competitive edge if you're open-minded.
Building the team is key too, not just PhDs.
Right. You need data scientists, sure, but also people who get the business side, the domain expertise. And with easier tools now.
Cloud platforms, open source.
You might not need a massive team of pure researchers. A mix of skills is often best.
Where do you get the data? In-house, open source, third-party vendors.
All options. In-house data is common, but might need cleaning. Open source is often free, but check quality and bias. Third-party data can be good, but costs money.
The main thing is crusting the data. Garbage in, garbage out.
Always. You have to ask, where did it come from? How was it collected? Is it complete? Any known issues?
And labeling data if it's unstructured. Tagging it.
Yeah, that can be labor-intensive, though AI tools are starting to help automate that.
The publishing company example predicting cancellations shows how you combine different data points.
Demographics, browsing habits, content preferences, building a model to predict churn.
But it also warns about choosing your variables carefully, like the mortgage crisis.
Right. Including or excluding the wrong data can have huge consequences. Flawed models contributed to the financial crisis.
The source lists common data prep techniques too. Filtering, handling missing values.
Noise reduction, scaling, dealing with outliers. Lots of steps to get data ready.
Sounds like a lot of work.
It often is. And data's rarely perfect. You need creativity.
Like the Bluevine CEO scraping websites because self-reported data was wrong.
Great example of finding clever workarounds when the data isn't ideal. How much cleaning you do depends on the use case, too.
And then there's ethics and governance. Super important.
Hugely. Data restrictions, legal reviews, privacy. The Facebook Cambridge Analytica scandal was a massive wake-up call.
Data needs to be handled with care.
Definitely. The source also mentions the curse of dimensionality.
Too many variables makes things complex.
Exactly. Especially for things like image recognition. Lots of dimensions.
The chapter ends with more data terms and stresses needing a data-driven culture.
Like Amazon or Google. But many companies still struggle with adoption.
Key takeaways. Structured versus unstructured versus semi-structured data, big data's V's, relational versus NoSQL databases, and the CRISP-PDM process.
Got it. A solid data foundation is critical.
Okay, chapter 3. Let's get into the mechanics of machine learning itself.
Right, where computers learn without explicit programming.
They ingest data, use statistics, find patterns.
Stitch Fix is the perfect example again. Personalized clothing picks based on user data.
And they succeeded even when VCs were skeptical at first. Shows the power.
Yeah, Katrina Lake, the founder, saw that gap. Collecting data isn't enough. You need to use it to genuinely personalize the experience.
Data science was the key.
Absolutely.
To understand ML, the source brings in some stats concepts, averages, standard deviation.
Outliers, the normal distribution. the basics of describing data.
These are the building blocks.
Yeah, descriptive stats summarize your data. Standard deviation shows the spread. Outliers are the weird points. Normal distribution is that common bell curve shape you see a lot.
Like IQ scores follow a normal distribution.
Good example.
Then there's Bayes' theorem. Sounds complex.
It can be, but the core idea is updating probabilities based on new evidence. Very useful in medical tests, for instance.
The cancer test example, true positives versus false positives.
Right. A true positive is correctly identifying the disease. A false positive is saying someone has it when they don't. Bayes helps calculate those probabilities.
And machine learning isn't just for Silicon Valley. It's everywhere.
Totally. Agriculture, energy, finance, healthcare, HR, marketing, manufacturing, sports. The list goes on.
Oil and gas drones, AI for recruiting, checking avocado ripeness.
Really diverse applications across the board.
And just like data, there's a machine learning process.
Builds on the data process. You visualize the data, look for patterns.
Select the important features or variables. That's feature engineering.
Yep. Then choose the right algorithm, fine-tune it, adjust parameters.
Test it on unseen data, evaluate performance.
And finally, deploy it for real-world use.
Using separate training data and test data is crucial here.
Absolutely. Train the model on one set, test its performance on a completely different set it hasn't seen before, prevents overfitting.
What's overfitting?
When the model learns the training data too well, including the noise, and doesn't generalize well to new data.
Got it. And there are different ways machines learn. Supervised, unsupervised.
Right. Supervised learning uses labeled data. The teacher gives the answers.
Unsupervised finds patterns in unlabeled data more exploratory.
Then there's semi-supervised, a mix of both, and reinforcement learning.
Like training through trial and error, rewards and punishments.
Exactly. Think game-playing AI, like for Go or chess or robots learning to navigate millions of simulations.
The source mentions semi-supervised for MRI interpretation.
Yeah, a radiologist labels some scans, and deep learning helps interpret the rest. Combines human expertise with AI scale.
And lots of different algorithms fall under these types. Naive Bayes.
Good example of supervised learning for classification. Simple, fast, used in spam filters. Assumes features are independent. That's the naive part.
Nearest neighbor, or KNN.
Another classification method. Classifies based on its neighbors in the data. Used for things like credit scoring. It's lazy learning. Doesn't build an explicit model beforehand.
Linear regression. That sounds familiar.
Shows the relationship between variables, predicts outcomes, like hours studied versus grade.
It finds the line of best fit.
Yep, using the least squares method. And the R-squared value tells you how well the line fits the data.
Then there's ensemble modeling combining algorithms, like the Netflix prize.
Exactly. The winning teams in that competition combined predictions from many models to get higher accuracy for movie recommendations.
Using techniques like boosting and bagging.
Right. Boosting builds models sequentially, weighting errors, bagging builds models in parallel and averages results. Powerful stuff. Though Netflix didn't end up using the winning solution.
Why not?
Various reasons, possibly changes in their platform, privacy concerns maybe.
Seems like the takeaway is, don't get lost in the algorithms, focus on the goal.
Precisely. Eric Colson's HBR article emphasizes curiosity-driven data science, fosters a culture of experimentation, learning by doing.
And he suggests hiring generalists, full-stack data scientists for smaller teams.
Yeah, people with broad skills who can handle multiple parts of the process.
So key takeaways for ML: the definition. Stats, concepts like outlier and standard deviation. Bayes' theorem, the ML process, training versus test data. Supervised, unsupervised, semi-supervised reinforcement learning, and specific algorithms like classification and regression.
And Pearson correlation for measuring variable relationships, feature engineering.
Yep, that covers the core ideas.
All right, now for the revolution. Deep Learning, Chapter 4.
This is where things get really interesting. Deep learning is behind many of the biggest AI advances recently.
Geoffrey Hinton called it great for classification problems with lots of data.
And Fei-Fei Li's work on ImageNet was absolutely pivotal, creating that huge, high-quality data set.
Even when academics weren't initially excited.
Right. Her persistence paid off. The 2012 ImageNet contest changed everything.
AlexNet. Hinton's team. Yeah, their system, using deep learning, just blew the competition away. Massive improvement in image recognition accuracy.
And progress on ImageNet just accelerated after that.
Dramatically.
Wow.
Deep learning models eventually surpassed human performance on that specific task. Fei-Fei Li's influence is still huge.
And this stuff powers self-driving cars, Siri.
Exactly. Traditional methods struggled with the complexity. Deep learning can analyze raw data, like pixels, and learn the important features itself.
Using neural networks inspired by the brain.
Right.
So what is deep learning technically? How's it different from ML?
It's a subfield of machine learning. It uses artificial neural networks, ANNs, with many layers, hence deep.
More layers means more learning power.
Generally, yes. Allows them to learn much more complex patterns from massive data sets, patterns humans might not even notice.
Okay, so ANNs are the basics. Units, weights, activation functions.
Think of units like neurons. Connections have weights that adjust during learning. Hidden layers do the processing between input and output. Activation functions add nonlinearity, which is crucial for learning complex stuff.
Feed-forward networks are common. Data flows one way.
Yep, input to hidden layers to output. No loops back within that specific network, though outputs can feed into other networks.
And there's specialized types of networks. CNNs for images.
Convolutional neural networks, inspired by the visual cortex, they analyze images section by section, looking for features like lines, edges, shapes. Very powerful for vision tasks. Jan LeCun did early work, but it took off post-2012.
And RNNs for sequences. Text, time series.
Recurrent neural networks, they have loops allowing them to remember past information in the sequence, crucial for language. LSTM's long short-term memory networks are a key type, good at handling long-range dependencies, used in Google Translate.
Then there are GANs, generative adversarial networks. Sounds wild.
They were pretty cool. Two networks compete. A generator creates fake data. A discriminator tries to spot the fakes.
They push each other to get better.
Exactly. The generator learns to make incredibly realistic images, audio, text. Ian Goodfellow's breakthrough in 2014, there's a whole Jan zoo now.
With these complex models, explainability becomes a big deal. Understanding why they decide something.
Hugely important, especially in critical areas like healthcare or finance. We need transparency. It's an active research area.
This source gives great examples of deep learning in action.
Diagnosing Alzheimer's years early in studies. That's amazing potential.
Better wind power management by Google DeepMind. Analyzing small earthquakes.
Even potentially reducing patient time in MRI scans or detecting financial fraud shows the breadth of applications.
But deep learning isn't magic. It has limits.
Definitely. It struggles with abstract concepts, common sense reasoning. It finds correlations, not necessarily causation.
And it needs retraining for new tasks. Doesn't easily transfer knowledge.
Right. It lacks that broad, intuitive understanding of the world humans have. Basic physics, for example.
So, key deep learning takeaways. The definition. ANNs, hidden layers, feed-forward networks, activation functions, RNN, SLSTM, CNNs, GNs, and explainability.
A powerful toolkit, but important to understand its strengths and weaknesses.
Okay, shifting gears again. Chapter 5. Robotic Process Automation, RPA, an easier path to AI.
That's how the source frames it. Software bots mimicking human actions for routine tasks.
Like data entry, scheduling.
Exactly. The UiPath story is incredible. Started small in Romania, pivoted to RPA, and just exploded.
Fastest growing enterprise software company ever by 2018. Wow.
Yeah, they hit a nerve. Companies wanted that automation for efficiency. The rise of AI and cloud really fueled it.
And Forrester predicts companies adopting automation-first principles.
Right, like the Kodak versus Instagram disruption, but potentially across more industries.
RPA is being supercharged by AI now.
Yeah, integrating AI makes RPA bots smarter, able to handle more complex things. It's often a good first step into AI for businesses. Lower cost, quicker setup someday.
What are the main benefits?
Higher customer satisfaction, fewer errors, better compliance, easier integration with old systems, efficiency gains, better data accuracy, scalability, cost savings.
And freeing up humans for more interesting work.
That's the idea. Let bots handle the repetitive stuff.
Downsides.
Can be brittle if the underlying software changes. Issues with virtualized apps sometimes. And employee resistance, fear of job loss.
So communication is key.
Absolutely.
Yeah.
And RPA works best for specific tasks.
Repetitive, structured, rule-based processes.
Exactly. High volume, prone to human error. Things where automation saves significant time.
Implementing it requires steps.
Identify the right functions first. Then really understand the process, maybe bring in consultants or use process mining tools.
Select the vendor, deploy the software.
Which can be relatively quick. And crucially, set up a team as center of excellence to manage it ongoing, handle exceptions, track performance.
And now there's cognitive RPA, CRPA, RPA with AI.
Right. Adds machine learning, NLP, lets bots handle unstructured data, understand documents, analyze sentiment, more intelligent automation.
The Microsoft example using Chiron for royalty payments.
Shows real savings. Automated 70–80% of the straightforward stuff. Humans handled exceptions.
So RPA takeaways. What it is, the benefits and drawbacks, best use cases, implementation steps.
And that it offers good ROI potential, making it a practical entry point to AI for many.
Right, Chapter 6, Natural Language Processing, NLP. Getting computers to understand language.
A huge challenge. Language is complex, nuanced.
The Microsoft Tay chatbot example is a cautionary tale, isn't it?
Oh yeah. It learned offensive language incredibly quickly from online interactions, showed how hard social context is for AI. Microsoft had to pull it fast.
Underscores that language is key to the Turing test, key to being human.
Definitely. And the challenges are immense. Ambiguity words mean different things in context.
Language evolves constantly, new words all the time.
Dialects, accents, sarcasm, humor, nonverbal cues, things computers just don't get easily.
It's so different from computer languages, which are strict and logical.
Exactly. Human language is messy, context-dependent.
So how does NLP work? Two main steps.
First, cleaning and pre-processing the text, breaking it down.
Tokenization, words units. Normalization, standard form. Stemming, root form. Lemmatization, dictionary form. Getting it ready.
Right. Then the harder part, understanding and generating language.
Using techniques like part-of-speech tagging, identifying nouns, verbs.
Yep. Chunking phrases together. Named entity recognition, finding locations, people, organizations.
Topic modeling, finding hidden themes, like latent Dirichlet allocation.
Right. Often using unsupervised learning to find those clusters of meaning.
The source mentions phonemes, basic sound units, and how voice systems evolved.
Big leaps thanks to machine learning and deep learning. Algorithms like LSTMs, RNNs power Google Voice, Siri, Alexa.
NLP has tons of uses. Chatbots for customer service.
First line of defense, saves money, frees up humans, voice assistants, even potential healthcare uses, like diagnosing depression from speech.
Content creation tools using models like GPT-2.
Yeah, generating text, sentiment analysis, understanding emotions in reviews or social media.
Effective computing AI, recognizing human emotions.
Like Ronel Caliubi's work at MIT and Effectiva. Emotion tracking, even in cars for driver safety.
Virtual assistants like Siri really show the evolution.
Started as a research project, faced huge challenges with ambiguity, book a 4-star restaurant in Boston, but eventually cracked it enough to launch.
And chatbots are getting more common for automating tasks, handling simple inquiries 247.
Big cost savings potential there.
So, NLP takeaways. The challenges, the two main steps, cleaning understanding, key techniques like tagging and topic modeling, and its many applications.
Yeah, and the fact that truly human-level language understanding is still a major goal.
Moving to the physical world, Chapter 7, Robotics, AI with a body.
Right. A robot needs a body, sensors to perceive, actuators to move, and some intelligence. Getting easier to build them too.
Two main types, telerobots, human-controlled, and autonomous robots, AI-controlled.
Early autonomous robots like Shaky at SRI in the 60s, 70s were groundbreaking.
It could move, sense, plan, the first electronic person.
Yeah, amazing for its time. Used early AI like strips planning, but funding died in the AI winter.
Industrial robots came next, but adoption was slow. Even Tesla struggled with over-automation.
Right. George Devol's Unimate was early, but large-scale factory automation is really complex. Sometimes less is more initially.
Which relates to the Moravec paradox.
Yeah, things easy for humans, walking, seeing, are hard for robots, and vice versa. Complex math is easy for computers.
Perception, mobility. They require sophisticated AI, good sensors. SLAM for mapping.
Exactly. Though reinforcement learning is helping robots learn to move and manipulate things better.
And MIT is researching ways to reduce the data needed for robots to learn.
Which would be a big help for adaptability.
Cobots, collaborative robots, are a big trend now, like Amazon's Kiva robots.
They're working alongside humans.
Yeah.
Amazon has over 100,000 Kivas in warehouses. Huge efficiency gains.
We're seeing robots elsewhere, too.
Yeah.
Brain cores, floor scrubbers, pill packs, pharmacy robots.
Yeah. Service robots in stores, automation in pharmacies. AI is enabling these applications.
But humanoid robots like Rosie the Jetson, still science fiction mostly.
Pretty much. Consumer robots are still fairly limited vacuums, some social robots that haven't always done well commercially. General-purpose humanoids are a huge challenge.
Asimov's 3 laws of robotics still come up, though?
They do. Prevent harm, obey orders. A useful ethical starting point, even with criticisms.
And cybersecurity is a growing issue for robots as they get connected.
Definitely. Cloud updates, IoT links, autonomous cars, they become targets. Malware, data security are big concerns.
Programming robots with AI is getting easier, though. Platforms like ROS.
The robot operating system, open source middleware, helps manage planning, perception, control. Makes development faster. Kind of an industry standard now.
So robotics takeaways. Definition. Telerobots versus autonomous. Moravec paradox. Slower AI impact than software. Cobots, cost barriers. Consumer robots are early stage. Asimov's laws and cybersecurity.
And innovative business models like robots as a service are helping with adoption costs.
Okay, Chapter 8. Practical steps for AI implementation. It's hard, even for big companies.
Needs care, planning, diligence. Failure is common, actually.
Two main ways to use AI vendor software or build in-house.
Right. In-house is much harder, even with vendor software.
Employees need to input data correctly. Garbage in, garbage out still applies.
Absolutely. Training is crucial. And being aware of risks. Bias, security, privacy.
The implementation process involves identifying a problem.
Building a strong team, selecting tools platforms, creating the model, deploying, and monitoring.
And thinking about the human-machine tango.
Yeah, how they work together. Humans for creativity, context, AI for data processing, prediction. Like the security robot example, bot detects, human response.
Need clear KPIs, metrics. Assess your IT readiness, too.
Legacy systems can make it harder, but even old companies like Symrise are using AI to innovate.
Building the team. Bezos' two-pizza rule. Mix of skills.
Right. Business, technical, domain expertise. A leader who bridges the gap.
Frameworks like TensorFlow and PyTorch help.
Huge ecosystems. Make building models easier. Python is the main language.
AutoML tools offer a simpler path for beginners.
Automated machine learning platforms. Drag and drop interfaces. Used even by tech giants internally. Lenovo Brazil used it for supply chain prediction.
And deployment is iterative. Learn, improve, repeat.
Exactly. Needs support, leadership. Recognize success. Tools like Alteryx can also help streamline workflows for non-coders.
So implementation takeaways. It's difficult, buy versus build. Data quality matters. Education is key. Manage risks, follow steps, human-tech collaboration, team building, iterative process.
Focus on solving a real problem and delivering value.
Finally, Chapter 9, the future of AI, excitement and concern.
Stephen Hawking captured that duality well. Huge potential benefits, but also potential risks like superintelligence or job loss. Hard to predict.
Autonomous cars are a big part of the future vision, but maybe further off than we think.
Seems likely. Huge market predicted, but complex driving scenarios, regulations, cost, public acceptance. Lots of hurdles.
We'll see them first in controlled situations. Trucking, shuttles, ride-sharing zones.
Probably. Waymo's Phoenix service is an early example, with lots of user education needed.
The US versus China AI race is heating up too.
China's making massive investments, aiming for leadership by 2030. A major global shift.
And the impact on jobs. A big worry. Not just low-skilled jobs.
No, white-collar professions too.
Yeah.
Legal research, contract review, AI is making inroads, new jobs will emerge, but disruption seems likely.
Parallels to manufacturing job losses, stagnant wages, wealth gap.
Those are the concerns being raised, leading to talk about retraining, education, even basic income.
Ethics and governance become even more critical. Bias, privacy, autonomous weapons.
Huge ethical debates. Bias in algorithms, data privacy, transparency, and robot killers, a serious concern with calls for bans, but a resistance from some major powers. Could lead to an arms race.
AI and drug discovery shows promise, though, speeding things up.
Yeah, analyzing data to find new drug candidates much faster than traditional methods. Startups like Incitro are attracting big partnerships.
Governments are getting involved, monitoring things like Alexa voice analysis.
Awareness is growing about how these systems are trained and used.
And the ultimate goal for some, AGI. Artificial General Intelligence.
Human-level intelligence across the board. Still likely many, many years away, though some predict it sooner.
But AI is already being used for social good, too. Anti-poaching, finding lead poisoning.
Lots of positive applications alongside the challenges.
So, future takeaways. Contrasting views, autonomous car realities, China's rise, job impacts, ethics, especially weapons, drug discovery potential, government involvement, and the long road to AGI.
It's a complex picture, requiring careful navigation.
If you want to learn more, the source lists some good publications and blogs. We encourage you to check them out.
And remember those key terms: ANN, backpropagation, Bayes theorem, big data, CNN, deep learning, NLP, RPA, Turing test, weak AI. Helps to know the language.
So wrapping up our deep dive, we've covered AI's history, data's role, ML, and deep learning mechanics, RPA, NLP, robotics, implementation, and the future outlook.
The goal was a clear, concise foundation, hopefully hitting those aha moments.
This is just a starting point, really. We hope it fuels your curiosity.
Keep exploring this fascinating field.
And one last thought for you. With all these advancements and ethical questions swirling around, what role do you see yourself playing in the story of AI?
It's definitely something we'll all need to consider.
Thanks for joining us for this deep dive. Hope you found it valuable.